Section 1.3, new functions from old functions. So we're going to consider a function, y equals f of x, and that could be any function. But when you take that function and do certain things to it, it creates a function that's very similar but looks a little bit different. So when we take a function and we add a constant to it, so that's what this c is, it's a constant. What that does is it takes every y value and it adds the constant to it. Now that constant could be positive or it could be negative, and so the function is going to go either up or down. So that would be a vertical shift. When you do the same thing, but you add that constant, and again, positive or negative, within the x value. So you're actually changing the x value, not the y value. You change the x value, which of course then, changes what the y value is going to be. But what happens there, it actually creates a horizontal shift. And you could kind of consider that because when you think about it, when you end up, adding c, you're changing the x value that goes inside. So it becomes the y value that's related to that other x value, and that's why you end up with the horizontal shift. Now, when you multiply, so now notice we have multiplication in here, to the x, so you're taking a constant, multiplying it by the x, and then putting that value into the function. What that's going to do is it's going to either stretch or compress the function. So stretch or compress, and that's going to happen in the horizontal direction. So you might take the function, and my H is not good, and it might take the function, so you have like x squared. When you put a value inside like that, like it might make it really wide or it might make it really narrow. When you take a constant and you change it by taking every y value and then multiplying it by a constant, you probably shouldn't be too surprised that this is also a stretch or a compress, but in the vertical direction. So it could take every y value and make it a lot bigger, or it could take every y value and make it a lot smaller, and so that's going to stretch or compress in the vertical. When you put in a negative value, we kind of already saw this. I mean, it depends on what happens, but typically, if you just put in negative x to a function, it's taking every x value and making it negative. So what happens there is a reflection over the y-axis, okay? Because every x value that you put in is now the negative x value. So you're thinking about the fact that you have this x here, but you're actually finding the y value for this x, so it flips it over the y-axis. And then conversely, when you do a negative of your function, that is also a reflection. And you can kind of imagine here, what's happening is all the y values are now becoming negative. So that's a reflection over the x-axis. So we'll take a look at what happens. We have a graph here. So we'll look at an example. We have a graph. And as you can see, it's an idea of an absolute value, but we don't really need to worry about that because we're just going to change this function. It's it's not the full function because it only goes from -1 to 1. But we have a graph of, it's called g of x. So we're going to do basically three things to this function. So notice we have a negative, notice we have a +1 inside the function, and we have a -2. So typically the thing to do would be to work inside and then move outside. So I'm going to notice that I have this +1 here. And what happens is, this actually does the opposite of what you think in the horizontal shift. So when it's inside like that, this is going to be a shift to the left 1 unit. So whatever value you put in is going to now move to the left. So you can do it kind of a couple different ways. I'll show you kind of the slower way. But so every x value now is, as you can imagine, you're taking every x value and you're adding 1 to it. And so you might think that that moves it to the right, but it actually does the opposite. So we're going to have a -2 instead of the -1x value. And we're going to have this whole thing shift 1 unit to the left. Now this is just the first step, so I'm not actually going to put it in because it's not done yet. But the second thing that happens after we shift it left 1 unit is, as you can see, it's got that negative on the outside of the g of x plus 1. And so this is the reflection over the x-axis, and that's just coming from our last thing there. So I'm just going to reflect the whole thing over the x-axis, so it's going to look like that. Okay. And then, as you can see, the last thing that we have here is this -2, so that's an example from the first thing that we looked at. And so that's going to be a vertical shift, and we have -2. So those ones are exactly what you think. Vertical shift down, in this case, 2 units. So I'm just taking every value and I'm moving it down 2 units. So I have this value goes down 2 units, this value comes down 2 units. So I don't need to come up with every value, I just need to do enough to where I can get the shape of it. So this is the graph of negative g of x plus 1 minus 2. So let's take a look at another one. It would be really good if you could pause and see what you can do with this, if you can get it or not. It gives us the graph. So notice we have the graph of the square root of x, but now we're going to do 1/2 the square root of x plus 2 plus 1. So we're just going to, as you should think about it, just take that and we're just going to transform it using what we're given there. So you don't actually need the fact that it's a square root of x. You don't need to think about that. But we do have something affecting the insight. So again, you can pause, try to do it, come back if you want. So this is going to be a shift left 2 units. So again, I'm going to work inside out. So I'm going to go in from where the x is. So that's a shift left of 2 units plus 2. So every value that I have, so I have 0, 0, so I'm going to have -2, 0. I have 1, 1. So that's going to go back and I'm going to have -1, 1. So notice my x values are going back. So I have this. Once we've done the shift left 2 units, now we will go to what is next to the part that has x in it, which is the 1/2. So now every y value, what that means is every y value is now going to get multiplied by 1/2. So it's a compress y values by 1/2. So notice we have a y value of 0, so that doesn't need to be compressed. Times 1/2 is still 0. We have a y value of 1, so compressing that just brings it to 1/2. And then the shape is still the same, so don't lose the fact that the shape is still the same. And then the last thing that happens is adding 1. So now every y value goes up by 1. So vertical shift up by 1 unit, by 1 or 1 unit, however you want to say that. And so that means that we do have a -2, 0. So now we'll have -2, 1. And we have -1, 1/2. So now we'll have -1, 1 and 1/2. And we'll head up here. And this will be our final version. So this is now this j of x right here, just using transformations. And now we'll just quickly talk about some function operations. So we just want to think about the fact that we have f of x and g of x. They're just functions. They have some sort of domain a and b. We just want to remember that there are things that you can do. So you can add 2 functions together, you can subtract them from one another, you can multiply them together, and you can even divide them. When you end up adding, subtracting, or multiplying, your domain is just simply the intersection. That's the symbol that I'm using here. Intersection of the 2 functions domains. So whatever is in domain A and is also in domain B is now going to be part of the, is going to be the domain of adding them, subtracting them, or multiplying them together. The only difference when you divide is to think about the fact about g of x. What can g of x not be? Cannot be a 0. So we just have to think about that you still have your intersection of A and B, but you also have to consider any times where g of x is not equal to 0. Okay, that's part of it. But if g of x is equal to 0, it's not part of your domain. So this last part here, for anybody that wants me to say that, is it is the set of all x such that g of x is not equal to 0. So any values where g of x is not equal to 0 is going to be your intersection of A and B. And that's just because g of x is fine by itself, but once it goes into a denominator, it can't be 0. So what you want to do now, if you want to just take a moment and pause and think about these, just creating these 4 functions here, just using what you see at the top, that would be great. If you want, hang on just a second and I'll remind you that when we have a function like x squared plus 3 of x, the domain of something like this is just all real numbers, and this is the symbol for all real numbers. This is a polynomial, it's quadratic, you can put in any x value you want and out's going to come a y value, so no problem there. For the radical square root function that we have there, 4 minus x, if you think about the fact that radicals cannot be negative if you want a real number, 4 minus x needs to be greater than or equal to 0. So that just means that x has to be less than or equal to 4. So I could also just write it opposite, x is less than or equal to 4. So we have to think about that. So if we add the 2 functions together, x squared plus 3 of x, if you think that this is going to look great and wonderful, it's not. It's just x squared plus, 3x plus the square root of x, 4 minus x. That's all it is. But when we think about the domain, so notice here's my domain there, and then I've got my domain here for g of x. The domain is simply the intersection. Well, the intersection of everything with x is less than or equal to 4 is going to have to be x is less than or equal to 4. So our domain is going to have to be all x such that x is less than or equal to 4. See if you can do the subtraction, the multiplication, even just set up the division again. All you're doing is writing it out. It doesn't look special. It's just to get you to think about it. But if you take f minus g, not surprising, it's just going to look like there's f of x, subtract g of x right here, and that's going to be all x such that x is less than or equal to 4, because all of those are all the same from the top there. The domain is the same for all 3 of them. Even multiplying them together, I mean, I don't want you to do a lot of work here. You might think you need to, but I just want you to take a look at it. But the point is, because of that square root of 4 minus x, we just cannot have anything where x is less than or equal to 4, because of course that is going to give you a negative in your square root. Now when we set it up for f divided by g of x, that's going to be just a polynomial on the top and a square root in the denominator. That's it. However, we have to think about what values would make your denominator 0. So if you take a look at that, you might notice, what can your denominator not be? Hopefully you recognize that if the denominator, if x was 4, then the denominator would be 0. So we don't want 0 in the denominator, so we don't want x to be 4. So the only thing that changes, because it still can't be less than 4, but now it also can't be equal to 4. So now we just want, as long as x is less than or equal to 4, we are fine. But we don't want x to be greater than 4, because that's going to give us a negative. So now we just want x to be less than 4. It can't be equal to 4, because that's going to give you 0 in your denominator. So it takes out one value that we have there. And those are some function operations with their domains.